Hello, thank you for joining us tonight. My name is Lorna Schumann. I am an educator at the Illinois State Museum. We are excited to be showing this program, Climate Change Through the Ages, with Samantha Rief, a geology professor at Lincoln Land Community College, and also to be joined by our own ISM Curator of Geology, Dr. Melissa Pardee, who will handle the questions from the audience at the end of the program. The museum currently has an exhibit in the Hot Science Gallery called Climate Change in Your Backyard. We invite you to come and visit this exhibit and learn more about what is happening in relationship to climate change in Illinois and where you live. With that, I will turn this over to Sam to help us better understand how climate change in the past happened and how we know that the current change is different from the past. Sam?
And thank you to the Illinois State Museum for having me here tonight. And thank you guys for joining me. I'm gonna share my screen quick and we will get started here. Okay, so as Lorna said, my name is Samantha Rief, and I'm a professor of geology at Lincoln Land Community College. I teach a variety of classes, and I teach two of them that kind of relate to really well to climate change. So one of the classes I teach is on natural disasters. And in that class, we spend about half of our semester discussing weather-related disasters like hurricanes and tornadoes and wildfires. And so, of course, we can't talk about those without talking about climate change. The other class that I teach that relates to this and really relates to this topic that I'm gonna draw on for this talk is a historical geology class. And in that class, we talk about the history of the Earth from the beginning to now. And so climate change is definitely something that we discuss in that class as well. So with that, I'm going to jump in and I'm going to start with, remember that I'm an educator. So this is going to be more an education kind of talk rather than a science kind of talk. So hopefully everybody's excited about that. So the first thing I want to make sure that we all have the same vocabulary. And one of the things that I see a lot is that people tend to confuse weather versus climate. This is definitely something that if you've watched the news in the last few years, we had a congressman who brought a snowball into Congress and said that climate change isn't happening because it snowed. So that was a clear indication of someone who didn't understand the difference between weather and climate. So weather, very simply, is energy moving around the Earth. The energy we're talking about is energy coming in from the sun. Energy comes in from the sun and penetrates our atmosphere, reaches the surface of the Earth, and that energy is what drives weather. So I have just a simple graphic here which shows you that solar radiation hitting the Earth and how it interacts with our atmosphere. So the key, the part I want to focus in on, is this part right here, the part that's absorbed by the surface of the Earth. So this is visible light coming from the sun, penetrates the atmosphere, hits the Earth, is absorbed by the surface of the Earth, and it's going to be turned around and re-radiated by the Earth, not as visible light. The Earth does not emit visible light, but it will be emitted as heat. And so that heat is the energy that's going to drive weather. So the ground, the air, the water are all heated up by excuse me, by this energy, and that is going to drive weather. Weather is going to be the movement of this energy through wind, through weather itself, through clouds and storms, through ocean currents. And so that's our description of weather. Okay. Excuse me. So we're going to talk about this a little later on, but what the Earth's surface is makes a difference to this number here. So we say an average across the Earth is that 50% is absorbed by the Earth. Bare rock versus water versus snow are going to absorb and reflect different amounts of that. Also, that number is going to be dependent on latitude, how much energy is coming in from the sun. It's also going to be dependent on season. But a good average here is 50%. Okay, and my dog is going to bark because the chipmunk is making noise outside, and my dog doesn't like the chipmunk. So excuse my dog. All right. So as this energy is being emitted and this heat is moving through the atmosphere, clouds form, wind blows. The formation of clouds also releases a little extra energy as well. Water changing from humidity, from water vapor, to the water droplets that are in clouds. That phase change actually releases some energy. And so that little bit of extra energy gives us severe weather. Okay, so the system is very well balanced. Energy moves from where there's lots of heat and lots of energy to places where there's less. And a little imbalance in that heat transfer and where the heat is localized, where the energy is localized, gives us severe weather. So when we talk about climate change, and climate change is the addition of extra energy, we'll talk about how that happens. So this is all of the scary things you see about climate change. We talk a lot about more severe weather, and we're starting to see that around the globe. And that's because of this extra energy. Okay, so on the other hand, climate, what we talk about when we talk about climate change, climate is the average of weather. So I just pulled a few graphics here. These might be graphics that you would see on the news or in magazines, and they all represent different climate sorts of data. Climate is the average of weather. So we could average temperatures, we could average wind speeds, we could average severe weather, we could average rainfall. It doesn't matter what we do, but we're going to take localized weather events and we're going to average them over a large period of time, usually at least a year. Often it's decades, sometimes it's centuries or even longer. So when we talk about climate versus weather, that congressman who brought the snowball into Congress, that was a localized weather event. We expect, even in a warming world, that winter will still happen. It will still get cold in some places. Washington, D.C. has winter, and so we expect it to snow. So saying that it's snowing does not negate what we're going to say about climate change. Okay, if the world happened to be cooling, as it has done in the past, we still expect it to get hot in the summer. If that's a thing that happens. Okay, so one localized weather event does not determine weather. We still expect, you know, we've seen climate changes happening, and we're seeing it happening, and we still see that it gets hot in the summer, it gets cold in the winter. So that's still around. The last thing I want to talk about before we get started with the talk, really, is something called the greenhouse effect. And this is something that most people have probably heard of. And I find in my classes that a lot of people assume that this is bad. A lot of my students assume this is a bad thing. The greenhouse effect is a natural cycle that happens on our planet. And it's actually a really good thing. So I have another simple graphic here that shows that energy that was absorbed by the Earth in that first graphic. This is that heat that's being re-released, okay? So that heat is re-released from the Earth and it comes up into the atmosphere where it heats the air, it heats the clouds, so it's absorbed. And then some of it escapes into space. And some of it, because we have greenhouse gases in our atmosphere, some of that heat is trapped. And so the downward arrow here, pointing back down to the Earth, is that heat that gets trapped. And we want that heat to be trapped. That trapped heat allows for the troposphere, the part of the atmosphere that we live in, to stay warm. It allows for water at the surface to be liquid and not frozen. Right now, our average amount of carbon dioxide, which is our main greenhouse gas, the amount of carbon dioxide in our atmosphere is about 0.04%, so 0.04% of our total atmosphere is carbon dioxide. And that little tiny amount of carbon dioxide is enough to keep the water at the surface of the Earth liquid and allows us to live and have evolved the way we did. So it's a good thing, but it's a teeny tiny amount of our atmosphere, right? So that tells us that a little bit of change, a little shift lower or higher in carbon dioxide amounts can make a big change to the effect that the carbon dioxide has in the atmosphere. If we have too little carbon dioxide, it gets cold, water freezes. If we have too much, it gets warm. Carbon dioxide is what we call a weak greenhouse gas. So it is fine at absorbing heat. It doesn't do it really well. There are other gases that occur naturally and some that occur unnaturally that are really good greenhouse gases, or really bad, that absorb heat much better or trap heat much better. So we'll talk about that as we move on. Okay, so those are kind of we know now weather, we know climate, and we know about the greenhouse effect. So the key here, the whole point of this conversation we're going to have is that human-induced climate change is happening. There is a scientific consensus. There is no argument against it. It is happening, and it has been for a while. There is much evidence. We'll talk about that at the end of the talk. There's much evidence for it happening. And so when Lorna asked me to do this talk, I thought about what I wanted to talk about. And I told you that I teach historical geology, which is the history of the Earth. And one of the arguments I hear for people who choose not to believe in climate change is that climate change is a natural thing and it's happened before. That statement is true. And I'm going to show you how, and I'm going to show you why it's happened before. But I'm also going to show you then at the end why human-induced climate change is different than the natural cycles that we see. So let's talk a little bit about the natural cycles so that you have ammunition to argue with your crazy uncle or whoever is in your life is a denier. Okay, so I'm going to start with, I think hopefully we've all been to the Illinois State Museum. And if you have, you've walked around the changes exhibit on the first floor. This is my favorite place in the museum as a geologist and somebody who teaches historical geology. This basically is my class that I teach. If you haven't been in the changes exhibit, it is an example of, it shows how Illinois' environment has changed through time from about 500 million years ago to present day. So these are the first two rooms that you go into when you go into the changes exhibit. The first one, everybody loves the diorama with the fish with the brush on its head. I don't know why it has a brush on its head. and we've got crinoids in here. And so obviously we were a shallow marine ocean at the time. And so you may think, oh, well, we were a warmer environment then, which is true, but this probably doesn't have much to do with climate change. It probably has something to do with where we live. So if in the changes exhibit in each one of these rooms, there's a map that shows where Illinois was on the globe at that time. So if you look right here, here's a little teeny tiny Illinois on the map. And so we can expect it to be warm because Illinois was in the tropics at that time, actually south of the equator. And so climate change is probably not the reason why we were extra warm at this time. When we go to the next room, this is the big bug room. This is my favorite one. So we have this diorama here of a very different environment with big tree-like plants. There's giant bugs, insects, excuse me. And so things look a lot different. But again, if we look at our map here, probably not climate change. We have Illinois here sitting right on the equator almost. So we would expect, again, for Illinois to be warm. So let's look maybe a little at the globe as a whole at this time, you know, over the course of this time period, and see what it is that we're talking about with natural climate change. All right, so here's a graph of temperatures, global average temperatures for the last 600 million years. So it's a long time. You'll notice, what I want you to notice in this graph is that temperatures go up and down. They do this a lot, okay? You might notice that the lines here are much more, what do I want to say? They're not quite as smooth. And this is mostly just because we have more data from here. So we have better data. Back here 600 million years ago, it's much harder to find, to get climate data. And so, so the numbers that we see are averaged over much longer periods of time. But we can still see the general trend, the climate trend of times when it was very hot, times when it was cold, and we can see that it goes back and forth. So when I talk about climate change through time, I like to call it, or I like to discuss the tale of two planets, okay? Because Earth basically goes through two periods over and over again. And so the two periods that we see are what we call ice ages and torrid ages. Okay, this picture, of course, is a little dramatic. The Earth is not frozen during an ice age. It's not on fire during a torrid age, but I like the visual of the change in temperature here. Okay, so let's talk about what these two are. The word ice age, or the term ice age, may confuse you actually, because when most of us think of ice age, we either think of a movie, an animated movie, or we think of walking through the museum and seeing the mastodons and the short-faced bear and that sort of room, the ice age room. So that's a time when we had continental glaciers, but it's not actually the definition of an ice age. So let me tell you what an ice age is. An ice age is a much broader term which deals with where the land masses are and sort of how the energy flow happens on the Earth. So during an ice age, we expect that near the poles, we're going to have land masses like continents. And we want that because that's how we can generate ice sheets. To generate an ice sheet like those glaciers that we think of when we think of an ice age, they're formed when snow falls on land and doesn't melt. So snow falls and doesn't melt, and then more snow falls and more snow falls, and we bury that snow, and the snow at the bottom becomes compacted and eventually compacts enough that it turns to solid ice. So that's only going to happen if we have continents near the poles where snow can fall. If there's open water there, snow falls and we don't get the same kind of ice sheets. So during an ice age, we have continents near the poles, and we also have land masses blocking the circulation of the ocean. So if we could imagine an Earth without any land, if it was just water, the ocean currents would flow around the equator and at different latitudes, but they would flow around the equator unobstructed. So that's the way they want to flow. And when that happens, if that were to happen, if we let the currents flow around the equator, then we don't have the transport of energy that we want, or that we have now. So think about the globe now with our continents where they are, and think about maybe the Atlantic Ocean. So the equatorial ocean currents flow from Africa across the Atlantic Ocean, and then they hit the Americas, right? And when they hit the Americas, what do? That current bends north. We call it the Gulf Stream. So the Gulf Stream is the equatorial warm ocean current bending around the east coast of the United States. So that warm water flows up the east coast of the United States towards the poles. So we're transporting hot water, we're transporting that energy up towards the poles. That's actually a good thing during an ice age, or that actually helps an ice age happen, because we're taking warm water and moist air, and we're pushing it north, which is going to help us generate more snow, because it's going to cool and then it's going to fall as snow. So it actually helps the process of snow falling and those ice sheets forming. So we'll come back to that when we're a little bit more about current conditions. But let's talk about the other side. Let's talk about the Torrid Age. So a Torrid Age is kind of the opposite of that. So during a Torrid Age, the land masses, the continents, are not blocking the equatorial flow of the oceans. So we get more flow and less water transporting up towards the poles. So we're going to get less snow at the poles. We're going to get more heat sort of staying at the equator. A Torrid Age is also going to be described by massive amounts of volcanism, okay, volcanoes. And we're not talking about volcanoes like Mount St. Helens or Pinatubo or even Tambora. We're talking about lots of volcanoes. So usually the kind of volcanoes we're talking about here are when we have areas of the crust of the earth that are pulling apart and generating all kinds of lavas and gases are escaping, and we're doing that close to the surface. So not at the bottom of the ocean, but close to the surface where those gases can get out. Those gases are going to be greenhouse gases. We're going to produce, there's going to be lots of water that comes out. There's going to be lots of carbon dioxide that comes out. There's going to be sulfur dioxide that comes out. There's going to be methane that comes out. And all of those gases are going to get pumped up into the atmosphere, which are going to raise the temperatures. And then we're also going to have our oceans are going to be warmer. We said that because we've got the sort of the energies trapped at the equator, so the temperature of the oceans are going up. And as the temperature of the ocean goes up, there are deposits at the bottom of the ocean called methane hydrates that form when deep water volcanoes erupt and produce those greenhouse gases, but the water around them is so cold that the methane actually freezes kind of into an ice. And so if we warm up the oceans, those methane hydrates melt, and that methane can be released into the atmosphere. And methane, as I mentioned earlier, is a strong greenhouse gas. So a little bit of methane goes a long way and raises the temperatures. So ice age versus Torrid Age. Okay, so there's one more thing that I want to mention. Again, if we're battling our crazy uncles, there's one more thing I want to mention about climate change that I hear a lot. That's part of the natural cycle, and that's something called Malenkovitch cycles. And I can make this really complicated, but I'm going to make this very simple. Okay, So the Malenkovitch cycles basically are a trend of how the planet moves around its orbit. When we think about the Earth moving around the sun or rotating around its axis, we often think about this very uniform cycle. We think about, the orbit of the Earth is sort of, we could draw it out and it's always the same. And so we think of this uniformity of the orbit. And over our lifetime, that's true. But in actuality, if we think about it, Earth over Earth's history, the Earth is more like a top, and it wibbles and wobbles all over the place. And so our orbit changes size and shape, our tilt goes back and forth, the whole planet just sort of wobbles around on its axis. And so there's a lot of this very chaotic motion that happens. It's not quite chaotic, it's fairly cyclical, but it is a lot more complicated than what we would expect. And so that's what these Malenkovitch cycles are. They're basically a graph or a trend of how the orbit changes or how the tilt changes through time. These cycles are huge. The change in the orbit is a cycle of 100,000 years. So these are big, long-term changes that happen in the Earth. The reason this matters is because if we change the orbit of the Earth or the way the Earth tilts, the amount of solar energy that hits the surface of the Earth, or where that energy hits the surface of the Earth, is going to change. And so these changes can change the climate. And especially if we have these three cycles line up. So if we look at these three graphs, we line them up on the chart here. And if we have times where we have the peaks all lining up, so we can have a time when we have extra heat because the Earth is close to the sun and it's tilted in such a way, and so we can have extra heat into our atmosphere, which can launch a torrid age. So you'll notice these cycles are long. These alignments don't always happen, and it takes a long time for us to get everything lined up. So, but the other thing about Malenkovitch cycles is that they're very predictable. We can kind of go back through time and we can kind of figure out exactly how these have changed, how these perturbations in the orbit and the revolution of the Earth has changed. And so we know what to look for. The climate change that's induced by a Malenkovitch cycle tends to be a slow change. It tends to be a change that happens over thousands of years. So it's definitely something that we see. It's definitely part of this, the conversation, but it's not a good explanation for human-induced climate change, which we're going to get to. Okay. All right. So those three things, we talked about ice ages, we talked about torrid ages, we talked about the Malenkovitch cycles. So let's talk about what's happening on Earth right now. So I'm going to go back about 56 million years. Okay. So again, our vision of an ice age is those ice sheets, but the Earth has been in our current age for the last 56 million years, and we have been in an ice age for 56 million years. Okay, so our temperature is below normal, below the average temperature of the globe for 56 million years. This started for a variety of reasons. So right before the dinosaurs died, all of the continents were all stuck together in one big chunk called Pangea. And right before the dinosaurs died, those continents started to break apart and they started to move. So 56 million years ago, enough of that movement had occurred that the continents were starting to land where we said we wanted continents in during an ice age, right? So we moved Antarctica to the South Pole. We moved North America and Eurasia up towards the North Pole so that there's land masses within the Arctic Circle. Let's see, we uplifted Central America. So before, as Pangea broke apart, North America and South America were separate. And then we had a collision that caused South America or Central America to form. And Central America, the closing of the Mediterranean Sea, all helped to create to help block the flow of the ocean around the equator. So now we have the ocean flowing up towards the poles. So the situations that we talked about for an ice age basically all sort of lined up and have been that way for the last 56 million years. A couple other things happened that allowed our temperatures to drop. So we formed continental glaciers that have ebbed and flowed in that time, but the formation of continental glaciers actually helps to lower the temperature. Earlier when I talked about the incoming solar radiation hitting the surface and being absorbed, I said that different surfaces absorb differently. So if I have a big vast area of white snow and ice, that's not going to absorb much heat. It's actually going to reflect that light coming in from the sun. So if I have big ice sheets, I've got lots of reflection of that energy. And so I'm not trapping that energy here. So that helps to lower the temperatures still more and more. So ice sheets lower the temperatures even more. The last thing that happened in the last 56 million years that is still affecting our climate today is the uplift of the Tibetan Plateau and the Colorado Plateau. So the Tibetan Plateau happened when India and Eurasia slammed into each other, created the Himalayas, created this big raised area. And the Colorado Plateau happened, it's the southern part of the Rocky Mountains, so the same collision that formed the southern Central America, uplifted this area. And what those two things did is they deflect the current of air that moves around the globe. So again, if we think of the Earth without all the continents, the air currents would move in a circle just like the ocean currents did. So just like having continents deflect the ocean, the Tibetan Plateau and the Colorado Plateau deflected the jet stream. So the jet stream is an air current that wants to flow in a circle around the globe. And so those uplifts cause the jet stream to get wobbly. And so it allows for colder regions much farther south than they would normally be because the jet stream has these big dips in it. And so it allows that cold air to flow down. And so that also helped the ice sheets form and move much farther south than we would normally expect them if we didn't have these big land masses in the way. All right, so let's zoom in a little bit more. So this climate data is for the last 40,000 years, excuse me. So we've zoomed in a lot. This is since the last, so this is within the ice age, but we can see some interesting things. This graph, just so you know, is average daily temperature over Greenland. Okay, doesn't really matter. It still shows the trend I want you to see. So if we look at this part of the graph here, we see that an ice age is very erratic. So we can see that we have temperature shifts by a few degrees. And again, this is average daily temperature in Greenland. So this wouldn't be as dramatic. The temperature shifts wouldn't be as dramatic over the entire planet, but we'd still see these dips and rises, okay? And so we see that there's warm periods and there's cool periods. if you've walked around the Changes exhibit and you've been in that room with the mastodons and the ground sloth and the short-faced bear, you also, if you look in the little cubby hole around the corner, there's a tortoise. And there's a tortoise because we had warm periods as well as cold periods. So this really shows this really cyclical nature of warming and cooling that kind of goes on during an ice age. And then we have a change. And the change really happens over here. And it happens at about 11,000 years ago. And 11,000 years ago, we see a change where we have we don't have nearly as many of these cool periods. It's not nearly as cool, and the whole average temperature is going up. And so this is showing that we're naturally getting to the end of probably this last ice age that we've been in. So we're maybe heading towards a torrid age naturally. So, wait, I'm gonna go back. So the current average temperature of the globe is 58 degrees Fahrenheit. So all the temperature over the planet is an average of 58 degrees. When this warming trend started, the amount of temperature change that happens, what comes down to an average of about 0.1 degree for every 100 years. Okay, 0.1 degree for every 100 years is the change that we saw in this 11,000 years, in this fairly dramatic rise in temperatures. So that's not a lot of temperature change. It's a very slow amount of change. Within the ice age, some of these fluctuations that we see, the average maybe changes to 0.2 degrees per 100 years. So again, even when you're having dramatic shifts and changes and it's happening a little faster, it's still a very slow rate of change. Okay, so I'm zooming in again. This is the last 1,000 years of history. And so again, this whole chart is only a degree and a half. So this is not a lot of change. We can still see a general rising trend from 1,000 years ago to now. We do see a couple dips in here. One of these dips is caused by volcanism. Volcanism can cause heating and cooling, which is strange. If it produces lots of gases, it tends to cause heating. If it produces lots of ash, it tends to cause cooling. So this was a time where we had a little bit of cooling from that. And then this right here, the Maunder minimum, these actually, the maximum and the minimum actually refer to sunspots. And so during the Maunder minimum, we actually had very few sunspots and we had less solar radiation than we normally do. And so that this dip here is from this less solar radiation that we have. Okay. And then we see things heading up again. Okay, so let's zoom in one more time. All right, so this is the last 140 years. Okay, so from 1880 to now. So what do we notice? We notice that the temperature change here is definitely on the rise, right? So I've zoomed in and it's hard sometimes to see the graph that it kind of looks like the same rate of increase. But let's look at the temperatures over here. Over the last 100 years, we've warmed the average planetary temperature by more than 1 degree. So over the last 11,000 years, what did I tell you? It was 0.1 degree per 100 years. That's the reason I told you that. So this is 1 degree, actually a little more than 1 degree over 100 years. So that tells me that in the last 140 years, the temperature has increased 10 times faster than it has over the last 11,000 years. So what's different in the last 140 years than in the last 11,000 years? What's different is us, right? So down here we have a chart that lists the aerosols that are in the atmosphere and how good they are at trapping heat, excuse me. So carbon dioxide is a natural gas in our atmosphere. It's not very good at trapping heat. Methane is a natural gas in our atmosphere. It's much better. These down here, they're not, ozone is natural, but chlorofluorocarbons are not natural. They are produced in industry, and their ability to trap heat is through the roof. So in the 20th century, there is no natural cause. All those things we talked about sunspot changes, we talked about the Malenkovitch cycles, we talked about all of those things that cause changes, all those plate tectonic things. None of those things have changed. None of those things are in play here. The thing that is in play are the gases that are being produced from burning hydrocarbons and from industry. And those gases we are releasing in insane quantities, and a little teeny tiny bit goes a long way. And so this very fast and very unnatural change in temperature is 100% due to human causes. So what does this mean? So oftentimes when we talk about climate change, we hear about there's going to be more hurricanes, the ocean levels are going to go up. Here in Illinois, maybe we don't care about that. What we do care about, but climate change is going to affect us. And even though it's not affecting, even though we don't care, we care, but even though the ocean is not going to be the thing that affects us as much. So what does it mean? Average surface temperatures. This graph over here is average surface temperatures across the globe. Average surface temperatures for central Illinois are predicted to rise by about 40 degrees by the end of this century. Now that sounds insane. That doesn't mean it's going to be 120 degrees in the summer. What it means is that, again, averaged over a year, we're going to have less cold days. So our winter temperatures, especially our nighttime winter temperatures, are going to go up, and that's going to raise our global average, or our average temperature, and that's where that number is going to come from. So what does that mean? That means we're not going to see snow. We're not going to see as much snow. For sure, we're not going to see as much frost. Our soil right now is dependent on freezing over the winter. It's dependent on freezing for certain plants that grow here. It's dependent on freezing to kill bugs. So if you are very excited about not having cold winters anymore, I hope you really like mosquitoes, because mosquitoes and other bugs are not going to die in their yearly cycle. And so if you've ever gone to some place where you needed anti-malarial drugs, just know that that's going to be part of our lives in the future. Malaria, Zika, those horrible mosquito-borne diseases will move north with the mosquitoes that don't die. So our temperatures, our winter temperatures won't be as brutal, but that's going to affect the natural world, obviously. The other thing, the graph down here on the bottom is change in precipitation. So again, we're going to see probably an average of 2 to 4 inches of rain more by the end of the century. So that sounds nice, right? But if you look at this, if you kind of zoom in here, we're in the blue, which is going to show more, but places like Missouri, Kansas, Nebraska are going to have less rainfall, which means dust storms. If you haven't read Grapes of Wrath, or you haven't read it recently, you might pick it up because that is our future, and in our very near future. Again, the nice thing about the Grapes of Wrath and the Great Depression, or the Dust Bowls of the 30s, is they ended. It started to rain again, but this is not going to end, at least not anytime soon. So what happens when Nebraska and Kansas and Texas and Oklahoma become Dust Bowl states? People have to leave. People have to move, just like they did in the 30s. So we now have climate refugees, and not just here, but look at all the places that are orange on this globe. So climate refugees are going to be a thing. When droughts happen and people are moving, that also tends to exacerbate other problems. So wars tend to become more during droughts and famines. So again, look at where these orange areas are, and places that are already tense will get worse. We will have more rainfall, but because we'll be close to those Dust Bowl states, we will start to see dust storms, and those can be damaging and deadly. Drier air in places like California and Nebraska and Texas means more wildfires. If you've watched California in the last few years, it's hard to imagine more. So this is going to have a very real consequence to us here in Central Illinois, and very soon. And it already is affecting us. If you've lived in Illinois for any length of time, you have seen these changes happening. Our winters aren't as severe as they used to be. The amount of time that the ground is frost-free is lengthening. We tend to have warmer winters than we used to have, and especially warmer nighttime temperatures. There's more heat being trapped in the atmosphere, and so that means our night times aren't getting as cold as they used to, because there's more heat in the air. We have longer growing seasons. That's nice. But we're all going to die of mosquito carrying diseases. You also might have noticed that your flowers that you plant in your yard come up earlier. Birds are migrating earlier. Butterflies are appearing earlier. And so there's definitely a general shift in the natural world as well. So it's not just that the oceans are rising, but everything that we are used to doing. We grow corn in Illinois. And that may not be something that we can do, or we might be able to grow more corn. I don't know a lot about corn, but this is something that affects everybody in every aspect of our life. The food we eat, the water we drink, everything is affected, and is already showing these effects. So again, climate change is here. It is happening. We are causing it. And so I don't have a lot of this. I could do another talk on, and what do we do now? But I will, I'm going to end this here, and Melissa's going to help me with, if you guys have questions, we'll have some questions, and we can talk more. Okay, so I'm going to turn off my screen, and hopefully Melissa will come on.
I'm here.
Hey.
Great talk.
Thank you.
I learned, I have a background in geology,
Yes.
in earth science, and I just did this exhibit, and there's still a lot to learn. There's a lot of things that are going on with the planet, and it's not simple, and it doesn't really fit in a soundbite. And so, yeah, it's nice to have this opportunity to kind of talk about these different things that affect climate kind of on a deeper level. And yeah, if teachers have, or any of the participants have a question, go ahead and either pop that in the chat or into the Q&A, and we'll field those. I had a couple of questions myself.
Oh, no.
No, I was wondering if you could talk a little bit more about how the movement of the continents impacts climate, not just in blocking circulation, but they're, physically being a continent there, but like mountain building, for example. You mentioned that a couple of times. What does mountain building have to do with climate? I think people don't usually think about that.
Okay, yeah. Most people have heard of plate tectonics before, and I know because when I talk about it with my students, they all go, oh yeah, yeah. And most people just think of sort of puzzle pieces just sort of moving around and doing things. So certainly localized climate changes, because we saw Illinois used to be below the equator and then on the equator, and now it's above the equator. So that kind of thing changes. But also when we collide two land masses and generate mountains. I talked about how it changed the jet stream, so that certainly is an effect. But also, a mountain is now a barrier to any kind of weather. So if you've ever been out west in the mountains, I suppose out east too, but I always think of the mountains out west. If you go to San Francisco, it rains all the time. And if you go across the mountains to Sacramento, it doesn't rain nearly as much. And so mountains are one of the reasons why. So wind coming off of the water brings moisture with it. So San Francisco sits right on the water, and the moisture comes in with it. And then because San Francisco also sits right where the mountains are, as the wind comes across, it's wet, it hits those mountains, it has to rise up. And when it rises up, it forms clouds, and those clouds then generate rain. And so it rains in San Francisco. When that wind then goes over the mountains, it's dry. So yeah, if you've ever been to San Diego is beautiful. And if you go over the mountains, it's a dry and barren desert. And that's because that water all gets dumped in San Diego and it doesn't get dumped on the other side. So yeah, building mountains forms barriers. And so a lot of Illinois or a lot of this area in the central part of the United States changed a lot when the Rocky Mountains were uplifted, because weather that used to come across the open plains out to the ocean, when the Rocky Mountains were uplifted, that weather stopped. And so that changed a lot of the rainfall and stuff here, and changed habitats and types of animals that live here for sure.
Yeah, that's really interesting that something kind of so far away on the other side of the continent can have local effects.
Absolutely.
Yeah. I have a question that so what's a change related to clement that you personally have observed, like that stands out to you, like in your life?
Yeah. Well, I grew up here in Illinois, and I moved away and then I came back. So I definitely see a difference. I do see a difference really in winter. When I was a kid growing up here in the 80s, we had snow days. It was cold. When it would snow, the snow would stay on the ground for weeks, right? You'd build a snowman and it would still be there and a month later. And now we have snow, but then 3 days later it's 70 degrees. And so I see, instead of there being winter for a long period of time, we get these ups and downs a lot more. And so I noticed that. Also, I remember, when I was a kid, trick-or-treating, and usually had to wear a coat. My mom would always make our outfits so that we could put warm clothes underneath them. She was good like that. And now, half the time trick-or-treating is, it's 80 degrees and you could be out there in shorts, right? So you definitely have seen winter starting later, for sure. I'm also a birder, and I do notice when birds arrive is much different than it used to be. So
okay.
Yeah, and as much as a few weeks for some certain birds. are actually arriving earlier in their migration. So
Interesting. Yeah.
Yeah.
Do you happen to know offhand, like any birds that that are arriving sooner than that people might maybe have seen in their yard that?
I would say hummingbirds, probably 40 years ago used to arrive like the end of April, end of April, and now they arrive middle April, or even sometimes a little earlier than that. The warblers, if you're a birder, those are the birds that we all go out and look for. And warbler season sort of starts in the middle. It starts beginning of April, and peaks at the beginning of May. And that's at least, the peak is moved about a week, probably in 40 years. So yeah. And you think of birds, we heard all kinds of things about, birds migrate by sight or by whatever, but the fact that they know, even though they're in Central America, they know that it's warm enough and there's bugs and there's stuff. It's amazing that, like, I don't know, do they get an email? Are they checking the weather? I don't know what they're doing, but somehow they know that it's okay to come. And that's fascinating.
We have a question here. How has the change in temperature affected insects?
So, from what I know, we don't have as much time that the ground is frozen, and the frost line doesn't go as deep as it used to. I actually had a fence put up in March, and most years you wouldn't be able to dig holes in March, and I moved some plants and did some things like that. So the frost line is it's in the ground less, and it's doesn't go as deep. So most insects, either a lot of them burrow into the ground, or that's where their larval stage is, or things like that, like cicadas or whatever. And what do I want to say? The good ones bury themselves, like cicadas, they bury themselves to a certain depth so that they know that they won't get frozen. And now they don't have to go as deep. But the bad insects, the things that we don't want lots of, like termites and things like that, they tend to get frozen and killed. So then, there's less of them, not that we lose them all, but there's less of them, and mosquitoes and things like that too. And so if we aren't freezing the ground for as deeply and for as long, we're less likely to kill a lot of those sort of nasty bugs. I spend a lot of time outside, and there's gnats and mosquitoes out, on warm days in February, because, we're just not getting that kill. And so, as I said, Zika for sure, and possibly malaria. These are definitely things that are going to move north. And so, you kind of hear about those in places and go, I'm not going to go to Central America. I won't get malaria, but you might get it in Florida now, or you might get it in, So, it's definitely going to change our futures.
From an educational and a teacher standpoint, what have you found that, so in talking about climate change in your courses, what have you found that students are most receptive to, as far as learning about climate change, maybe even like changing their mind about their understanding of whether it's happening or why?
So I don't get a lot of argument that it's not happening, which is good. I don't think a lot of them have thought, at least because I'm teaching college students, I don't think a lot of them have spent a lot of time thinking about how bad it is, or how it really affects them. Because on the news, and when you hear about it, it's always about the oceans are rising, and the oceans are acidifying. And in Illinois, children, that's not something that's on their radar. right? That's far away and that's not related to them. So I teach this disasters class, and we go through all of these weather disasters, and most of them, a lot of them are far away, but we start to bring it into here. And I always end that class with a discussion about what can we do, because I find that the class is very depressing, because after a while they're like, oh my God, we're just going to die of everything. Okay, so what do we do? And I think that's the point where you can bring them in, because I have, it's an open discussion where they can go out and find stuff, and they find some of the coolest, these people are doing this great thing, and these people are trying to invent this thing to, and so it kind of gets them involved with the, what can you do? And then I try to stress your power as a citizen of the planet is in electing officials that care about this, that electing officials that understand the science, and that we need to do something about this globally. And so I think at the end, I give them that ray of hope and hopefully encourage them to get involved. I also make a real strong point, and I think this is really important, is that just like talking about climate change and how complicated it is, and how many different factors there are, the solutions that people are offering up are also just that complicated. So if you find YouTube videos about how to fight climate change, they will say, eat less protein, eat less animal protein. They will say recycle and use less gasoline. So my students say, okay, I'm gonna become a vegetarian. Okay. So if you eat quinoa that was grown in Peru versus a chicken that you grew in your backyard, which one of those has a smaller carbon footprint?
Yeah.
So, it's not as simple as they make it. I'm going to drive an electric car. That's great. You got to plug in an electric car. Where does your electricity come from? Mine comes from a coal burning power plant. Right?
Yeah.
So most of ours do, right?
Yeah.
And so I try to make sure they understand that, the simple solutions aren't as simple as the internet would make you believe too. Yeah.
I think, what you said about, bringing it local, and providing examples to, your classes about, polar bears, it's sad, and the ocean. Right. But like I think a lot of people don't quite realize that, exactly what is happening here in the middle of the country. And so I guess to wrap up our discussion here, we do have some local examples in the new exhibit. And they all pertain to either Illinois or the Midwest. And so I invite, you to bring your students. I invite the teachers that are participating to please bring your students, and, talking about those, what people can do. I'd love to hear, people share with the museum, the things that they care about, and, how they are personally taking some, personal responsibility for, taking care of the planet. And I really wanted to thank you for presenting today as well. Yeah.
Well, thank you for having me. This was fun.
It's always fun. Yeah.
Yeah.
Lorna, did you have anything you wanted to add?
Just a couple of things. First, I want to thank you, Sam and Mel, both for being here tonight and helping us through this conversation. Thank you. I believe everyone learned a lot from it. Good. And it really helped encourage people to understand what really is going on.